the stream and see what the heck happens. We are back at it again. We are writing a bootloader of sorts. Let's see here. I'm also verifying while I'm talking that this is in fact streaming. The only way to know for sure is check on the phone. Boom. Okay, cool. We are writing a bootloader, and we've been doing so for the last 2 weeks. We're trying to kind of document the learning process, and also learn at the same time. If you're going to document the learning process, we're probably going to learn something. And what I am interested in learning here in this series, right now at least, is understanding what happens if we peel back the abstraction layer that is the kernel. No more kernel, we don't have that anymore. And instead, we've just got some hardware, and we've got some x86 running on some hardware. There's some sort of BIOS thing here. We are writing our bootloader. We're running initially in 16-bit mode assembly because I guess that's just what the CPU decides to, the mode that the CPU decides to start in, which has some caveats. We learned a little bit about, segment registers. We've learned about what's called an ISR, an interrupt service routine. This is something before this series I didn't really know a whole lot about. And in the last video, we got two ISRs set up. We got this timer ISR, which happens literally every 18.2 hertz. So 18.2 times per second, this fires off somehow, just, aggressively. The CPU just changes where the program counter is pointing at 18.2 times per second, and it points it at this instruction right here because that's the instruction pointed to by this label, and we put that into this address right here. So this address right here is where we put the timer ISR handler. So at address 8 times 4, the size of these things are 4. They're 4 bytes big for each of them, and we're in 16-bit mode assembly, which means we can only write out 16 bits of memory at a time, or 2 bytes. We write the first 2 bytes here, which is this, and then the next 2 bytes is the segment register. And then we do the same thing for the keyboard. So then the keyboard, instead of being the 8th element, it is the 9th element, and we do the same thing. So every 18.2 times per second, I believe we set it up where we're writing an A, which has, I think, like a yellow background. We'll test this here in a second. And also, we're handling whenever the keyboard does something. We read the scan code from the keyboard controller by doing this in AL60 thing, and we print that thing by writing out to video memory. So video memory is located right here, and we're all set up to write out. We got to translate from like the QWERTY layout. We learned this in the first video. Turns out this thing coming in from the hardware is not like ASCII code points. It is instead like QWERTY. So literally, you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. I mean, maybe that one makes a little more sense, but in order, right? This is just a giant table. Each little thing is 1 byte, 1 byte, 1 byte, 1 byte. We've got a Q followed by W, E, R, T, Y, right? And I don't think we filled out this entire thing, but we got at least the top half of the keyboard filled in. We also learned we have like 512 bytes, or maybe we didn't learn that. I've kind of been asserting that our bootloader gets to be 512 bytes. I kind of know that, I think, from an operating systems class that that's the case. Somehow you can expand it, presumably, right? Computers need more than 512 bytes of memory of code. So somehow we can expand this thing. But for the time being, and so far in this video series, we are operating in a 512 byte thing. So let's actually go ahead and go into boots. So we've got this bootloader we were looking at. We've got run.sh, which we have some comments for, kind of getting our monitor to be visualized. We've got some command for how to build our bootloader, this 512 byte thing. We've got QEMU to boot this thing. So all we're doing is we're booting it. This means GDB is accessible. And this is our hardware, or one piece of our hardware. We're putting in, like a hard drive, and that hard drive has bootloader.bin on it. And bootloader.bin, as I just said, was 512 bytes. So boot up this thing, we can through no VNC, and this thing exposes a VGA monitor over VNC. We use no VNC to see it in the browser. We can see our monitor. And that's kind of where we're at so far. So I don't know yet what I want to do in this video. I'm thinking I want to figure out what's going on with networking hardware. Do I already have networking hardware plugged in? And if not, maybe doing whatever the bare bones minimal thing is to plug networking hardware into this thing. And maybe we'll start seeing some packets. That's one path that's on my mind. Maybe that's going to work through an ISR as well. Maybe. Maybe one of these ISRs would be able to, trigger every time a packet comes in. Not totally sure. We're going to figure out what's going on there. And yeah, I think that's kind of what we're looking at. So we might go the networking route. We might also go the how do we expand beyond 512 bytes? How do we leave real mode, go to protected mode? These are all things on the horizon. Let's go ahead and make sure that everything still works. So if I do this and this, so we want this, we want to run that on the side, never need to look at that again. Run.sh, now we've got this serving. And if I go to this URL, we should be able to see things. Cool. Yeah, we see our A's are flooding in. And let's actually take this, this, put that there, put that there. Now we got our monitor over here. We got our code over here. Maybe we even shrink this a little bit. Don't need too much monitor. Cool. And I can also type because all of this is asynchronous. Right, I can type, and every second an A is coming in. We kind of got like two things happening simultaneously in some sense, even though we're just running on one core. Really, it's not that we have two cores that allows us to have two things happening simultaneously. Instead, it's that everything we're doing is asynchronous. We're in this busy loop where we're constantly just halting the CPU and waiting for an interrupt. So a timer interrupt or a keyboard interrupt. And that's where we're at. Now the question is, and the question I want to investigate maybe, is how do I hook into networking? So if I want to do that, we're going to need a few things. Somehow we're going to need the ability to send a packet at this thing. And what I mean when I say that is, I closed another terminal, but we'll create another terminal here. PS1 equals that. CD dev boots. What I mean by that is right now we have this QEMU process running, which kind of is our virtualized machine, our VM. I need to be able to talk to this. If I want to do networking, I need to be able to type like netcat 10001 port 80 and say something. Well, what the heck is running on port 80? Wait, what? Who is 10001? Oh, I might be talking. Oh, I think I'm talking to this. Am I 10001? I put that as a random IP address. Okay, we are in fact talking to this no VNC thing. All right, detour. Somehow though, maybe instead we'll say, localhost on port 4242. There's nothing there. So somehow we need to set up some routing so that packets make their way to this virtual machine as well. And then also on the bootloader side, we need to be able to analyze these packets in some way or have some sort of understanding of these packets. So let's go ahead and investigate that then. I think what I'm going to do is I'm just going to straight up take all of this, go to ChatGPT. Another thing we're doing in this series, we're using lots of ChatGPT for learning. So I'm not afraid of ChatGPT. We're going to say, let's give it the context of that. We'll give it the context of our run.sh, or at least, this part. I want to now support networking. How can I receive, let's say on the host, I want to run something like netcat 127.0.0.1 and see the packets show up in the VM or some other IP. I'm not too picky. And let's zoom this in a little bit also. Okay, nice ChatGPT. What the heck is happening here? Let's just start a new session. Sometimes ChatGPT gets a little uppity. What the heck? Hello? What's happening? Did ChatGPT go down right as I decided to make a video? Hello? Okay, that model works. Hello? Okay, cool. All right, we are momentarily switching over to 4 instead of 4.0 for this video, or at least for now. Should be basically no difference, but sometimes it is what it is. It's going to be slower, but maybe it's more intelligent. I don't really know. Okay, anyways, back to the task at hand. Step 1, configure QEMU to use a user network. I'm familiar with QEMU enough to kind of know what it's talking about here. At least a little bit. So similar to how we added a drive, we can add a device, which is an E1000 network device to my VM. Netdev user netdev sets up a user mode network with TCP forwarding. There might be, I feel like there's a simpler command than this. Isn't there? I do man QEMU system x86 64 and I search for net. I thought there was like dash nick. Yeah, this. So there's this, or you could just do this. Just kind of like, instead of having a netdev and a device, a nick is just like kind of all in one. I think that's what I want to do. So I guess this makes sense that it just has a MAC address, right? We're not saying that it somehow has an IP address. Oops. Host forward. We might need to do host forward though. Do we need to do host forward? I'm trying to remember. Dev. Maybe we need the more complicated one. Somehow the packets actually need to route to this VM, which means we need like QEMU itself to open up port 4242 so that when you hit 4242 on your host, QEMU is the thing listening and it is able to enter that virtual machine. Since your bootloader runs, okay, blah, 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 blah. there a way to do this with -nic? Probably don't need to care about this. But I would like it to be as simple as we possibly can be. Yeah, I guess you can do the host forward inside of that -nic. Yeah. Wait, did I already see that? No, they were configuring a MAC. Because we don't need to configure the MAC, though. We don't really care what the MAC address is. But the crucial detail with this host forward, which might seem unintuitive, is again, if I start netcatting at some port, like it needs to know where it's going to go. And based on the fact that we're on this host, things will go like there's a list. If QEMU itself is listening on port 4242, it's going to, the Linux networking stack will be willing to take that packet and throw it into this process. And then QEMU will take that packet and virtualize it or whatever, make it appear on this device, et cetera, et cetera, et cetera. So I think this looks good. Let's roll with that. I think our code should still just work. Well, this was our old bootloader. Yeah, before we start, actually, let's go ahead and copy bootloader.asm to bootloader-2.asm. You know, we'll just, who needs Git when you can just have backup files like that? We don't really care about the backup, but just in case. Maybe we'll call it makedir and move these previous bootloaders into prev. Move bootloader 2 into prev. Okay. Now let's go ahead and add. Let's go ahead and add our -nic, which is user that's emulating this type of device, host forward 4242. Sure. So we'll only support, I think, TCP on this port. Maybe there's a way to get all network traffic forwarding at it somehow. I don't know what that would look like. But we're going to roll with this for now. We're going to say keep it simple. One port is going to be good enough. All right. Let's see, make sure that if there is anyone that has any urgent requests in the chat, we're able to see that. Skip tutorial, that. Cool. Awesome. All right, let's go ahead then and make sure we still boot, right? We changed run.sh to now have this nic. Let's go ahead and run it then. Okay, things still work as expected. We just have new hardware. We're not using that hardware. The hardware has appeared. Now let's see what the heck ChatGPT has to say about how we handle these packets. Okay, yeah, we're going to directly interact with that networking card. Set up the networking card. E1000 registers for basic operation. Configure it to accept packets based on simple criteria, e.g. all incoming packets. Sure, well, let's see all incoming packets. Then we can do polling or interrupt handling. Well, in the first week we're doing polling because it's simpler, but you know what? Right now we're kind of liking our interrupt handling, so maybe we'll do that. Set up an interrupt service routine like you did with the timer and keyboard that gets triggered by network events. I like that. Or we could be simple and poll. Maybe the first thing we'll do is poll, and then we'll go, I don't know, we'll see. We'll see where this takes us. Okay. Would exceed the, you know what, I don't believe you. I think we can fit our networking stack in our 512 limit. I don't believe you. We're just going to continue. Don't we have like so much space? We got so much space. Look at this. I look at my bootloader.bin. Look how many null bytes I have. This, you don't think I could fit a networking stack in there? I don't believe you. We can fit a networking stack in there. Okay. Show me how in my bootloader I can configure my E1000 network card to receive all packets. How do I configure this thing? If it says it's quite challenging, stop saying it's challenging, just do it. Blah, 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 blah. Simplified approach. Sure. Just do it. We don't need to talk about why it's difficult. It's not difficult. It's just going to be a handful of instructions. Not difficult. Okay. Is this like, I'm realizing now how much I've grown to appreciate 4.0. It goes a lot faster. Just sitting here slowly reading. Maybe it's good for me though. I feel like I skip half the words in 4.0. Is it full featured OS? You'd use PCI enumeration. Okay. Do we need to do that? Maybe we should do that. What does that even mean to do PCI enumeration? Bootloader, you might hardcode values based on expected DM. Maybe we like hardcode values a little bit more. Reset and initialize the card, right to the control register to reset the card. Okay. Set up the receive array. Point the receive descriptor register to your what the heck does that mean? Okay, sure. Enable interrupts optional. In your case, as polling might be simpler, blah, 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 blah. Okay, what is this control register? What's the receive control register? Receive packets. Check the status. Set up an ISR, polling, check. Yep, that makes sense. What the heck is this? Oh, are these constant? Okay, sure. Don't know what these things are, but it's kind of fun. Assume ESDI. Weren't we using ES for video memory? Are we gonna have to deal with ES moving around? Yeah, we're using ESDI for my video memory. You want to use ESDI also for my packets? Can't we use something else? Or are we gonna have to, we're really gonna have to manage this, aren't we? That's all right. We got memory. We can save things, but okay, so it's doing ESDI plus base memory map. Okay. So we have memory mapped IO. Is this memory already like defaulting somewhere? Like E1000, we plugged it in, now it's memory mapped automatically? Do we think it's default memory map? Or EAX with this. So we want, okay, so we pulled something out of this piece of memory, put it there, ORed it with this, we turn this bit on, and then we move it back. So we, small delay here, or wait for reset bit to clear. What do you mean small delay here? I gotta like busy wait? Or wait for reset bit. Is this like a delayed operation? You're telling me as soon as this instruction's done, it's not actually reset? Set up receive descriptors, assume DSSI points to our descriptor array. DS to EAX, shifted 16, or KY. Descriptor count, size of a descriptor. Head and tail. What the heck is... So these all are clearly acronyms for something. Initialize, set the length of the descriptor array. Okay, so this location has the length. Okay. Here's what I want to say to this. First of all, we probably can't assume that my bootloader initializes that to ASCII video memory, or whatever the heck that's actually called. Where would it normally be if I use -nic? What address do we think it's going to be at? Here's a basic. It really likes to say basic approach. I just want code. Oh boy. Do I really need to scan? It's not going to just be somewhere like my nice video memory is. To determine the MMI, you would read its bars. What the heck is its bars? PCI access in real mode. Okay, whatever. Maybe we need to scan the PCI. Enable bit for PCI access. Bus number, device number. This is how you read a... Why are we doing so much like shift left, blah, blah, blah? Why, like, what is this? Can't we just shift left by 8? What's the difference? Don't understand that. Or dx with dh, function number. Inputs, PC, bus, device 3 function, read PCI, offset for bar 0. Is this, if I look at the man page, is this going to say something about PCI? Device VirtIO net PCI, but that's VirtIO. I don't think like do networking cards always go? Are they always PCI cards? Okay, here we go. Net legacy option to configure or create an onboard or machine network interface card. And it can connect it. Emulated hub with ID 0, the default hub, or to the netdev ND. The NIC is an E1000 by default on the PC target. Optionally, the MAC address can be changed to MAC. The device address set to adder, PCI cards only. The device adder is set to okay, so we can possibly configure that, and but it says PCI cards only, which implies that it might not be a PCI card. And name can be for PCI. You can specify the number V of MSI X vectors. Option currently affects VirtIO cards, which I don't think we're doing. That's like fancy efficient stuff. Set V equals 0 to disable MSI X. If no dash net option is specified, a single NIC is created. Okay, but where does it appear? Like, if it's not, I guess maybe one question would be if it's not a VC or PCI card, like it's not plugged into the PCI bus, which when I say that, I don't really know a whole lot. I also saw a question that previously popped up. Are you working on building a kernel? We're working on building out the ideas of a kernel. So we're just exploring the fundamental ideas that would go into a kernel. I don't know that we're going to build a kernel, but we want to know what are the core concepts involved in building a kernel. The host backend options are the same as with the corresponding netdev option below. The guest NIC model can be set with the model equals model name, model equals help. Hardware MAC address can be set. Yeah, we know this. But okay, so the question is, if it's not a PCI card, what other options are. See, I don't know hardware at all. Like I know PCI is like there's the PCI bus, right? It like plugs into PCI. I don't know hardware at all. What else is there besides PCI? Is there something? I assume there's something maybe more simple, more basic, and is that the default? That is the question. So it says these two are the exactly the same. This is netdev equals n1. Um, um, we can also do guess forward to make it talk the other direction, I think. I think we would do host forward and guess forward if we want bi-directional communication. Also, I guess it's some sort of .15 address. Okay. netdev. I think this tap stuff is how we would give it its own IP address if we wanted that, rather than just forwarding only like port 4242. Okay. But this is all host related networking details. Okay. By default, with how, what did I do? I ran, is this going to be PCI or something else? I really want to switch back to 4.0. Yes, in the QEMU setup you've described is indeed presented as a PCI device. So that could be a hallucination, but let's roll with it. This virtual network card uses PCI for its configuration and operation. Okay, PCI enumeration. So we're looking for, I'm imagining we're like walking memory and looking for something to the effect that says like vendor ID, like some of these bytes are gonna be like 8086 and some of these bytes are gonna be like hex 100 or something like that. Is there a way? Okay, so I guess the question is, so this is how I read a PCID word. Where, oh, this is an out instruction. Okay, this is what I was looking for. So we're not reading from memory, we're doing out and in. Send address to the PCI config address port, which is CF8. So basically if you do out, wait, this is EAX. What do you mean EAX? We don't have EAX. Someone's confused. Okay, let's see. Here's what we're gonna do. We're gonna half trust it. So we're gonna say out DX at the very beginning of my bootloader, right here. We're gonna do out DX this PCI config address and see what the heck pops out right here. How do I think if I want to catch this, we don't need that. I think we need capital S also in our run.sh. Capital S will make it pause right away. Okay, here's what we're gonna do. Run.sh. Oh boy. Is this gonna have to be like a move AL or move AX 0xcf8. How do I do other out instructions? Oh, this is from an AL. Can we take a 16-bit register, or is that going to be an issue? Please tell me that we can do PCI stuff in 16-bit mode. One way to find out. And if not, well, that will be our excuse for leaving 16-bit mode. Do I need to do capital? Oh, I think we just do capital S. That would imply lowercase s also. We don't need that guy. Okay. Capital S. Pause it right away. ls gdb x debug gdb. What? Guest has not initialized the display yet. Yeah, I know that, but can I not attach right away? Wait, is it? It's not uppercase X, is it? Nope. Wait, it's not EX, is it? That's to do, yeah. It's just X. GDB. Why can't I target remote this thing? Does dash capital S not actually work? You must type C in the monitor. Oh, I don't want that. Can I int 3 or something? Is there any way int 3 will work? We'll try it. I'm skeptical. I'm pretty sure that would register like in the same way as we can have interrupts this way. I think it would hit a different interrupt. But one way to find out if this simple approach for pausing right away will work. Otherwise, I got a backup plan. Lowercase s again. I don't want to figure out this monitor thing. There. Where am I? Yeah, my plan didn't work. This just triggered a different interrupt, and no one is looking at that interrupt. Okay, here's what we'll do instead then. Simple little hack. We will just put this in our loop right after our halt. We're going to do this. We're going to do this. Then we're going to look over here, and we're going to break at plus 1e. Break 0x7c1e, right? Right at this instruction. Okay, cool. What the heck is it? Oh, we can't trust this too much. This is a lie. It's disassembling it as 32-bit. Wait, this thing said that this was chill. Yeah. Okay. So we got to step. So we're at 21. If we step one more, it should be in DX. Okay. So an 80 came out. What does that mean? Showed up on DX. Send address. PCI. What is this doing? So we put CF8 in here, and out came hex 80. What does that mean? What is all of this other stuff, though? I feel like this isn't doing anything. Explain what out dx is supposed to return into dx. I got a hex 80. Instead, it writes data. Oh, it is an out instruction, not an in instruction. Oh. Wait, so then what the heck is this doing? You're telling the PCI controller, I want to access this particular device, this particular function, and this particular register. Wait, do I have out instructions in my bootloader already? Out. Acknowledge interrupt handler. So I write to 20 with a, okay. Okay. So we need to dynamically construct where we're outing to, right? Is that what this is saying? We want to out to DX, which is figured out through all of this stuff. Okay. Okay. So can we not make this so complicated though? Like what are we expecting DX to be? Let's not have a function named read PCI dword. I want to just directly read for bus 0 device 3 function 0 bar 0. Show me the couple instructions for my out instruction. Like I just want to just make this single instruction happen without making this all dynamic. What exactly am I doing? To directly read the base address register for a PCI bus 0, blah, 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 blah. Okay. Constructing the PCI address. Enable bit. So we're doing an enable bit, 31st bit. But this is a 32-bit. It is an issue. We don't have 32 bits. Can I interact with this thing in 16-bit real mode? I don't have 32 bits. Okay, this makes sense also. This goes right here. Yeah. But, okay, we're going to need to figure out how to... I don't think I can do this, right? I mean, we can try, but I'm pretty sure it's going to tell me absolutely not. Here you go. Let's see. Assembler, do you assemble? What? You can interact with EAX? Does that actually work? Now I'm even more confused. It says it assembled. Wait, in 16-bit mode, do I have access to 32-bit registers? What? I don't have access to 64-bit registers, right? No. But I guess I got access to 32-bit registers. All right, we'll roll with it. Okay. So Here's what we're going to do. We're just going to hard code things. Move dx this, and then this. Okay, so we halt. Okay, so this is our out instruction for reading from bus 0 device 3. Why do we think it's device 3? Who decided it's device 3? Where does the 3 come from? That's like a magic number. Commonly, I guess it's just normally device 3. We'll see if that's true. Okay, so this is how we bit pack this thing to come up with this magic number. Got the high bit set to a 1, which makes sense. Or, I mean, it doesn't necessarily make sense, but we can roll with it. These bits are how you select our bus number. Okay, so it's just bus 0, device 3. These are our bits here. We can see we're shifting left by 16 because that's where these bits start. And then we can't take up too many bits, but this is definitely not taking up too many bits. This isn't taking up too many bits either. Shift that. 0 function number, register number. Okay, I still don't know exactly what we're doing, but I think we're saying like, okay, PCI person, I want to read from this. And in order to say I want to read this like PCI thing, I say, okay, out to the config port, and then in, like, this will give me my result, basically. This is like selecting what I want to read. This is reading it. It's like, you could imagine this going through memory instead, but instead it's like an out instruction and an in instruction, which I guess some things just aren't memory mapped. And if it's not memory mapped, I still don't fully know like why CF8, like who set up that it's whatever. Somehow CF8 is magical, but that is okay for now. So we'll do that, and then we will do this. Actually, let's just copy this all. Now EAX contains the value of bar 0 for the specified device. So the question is, what should it be if that means we definitely just read my PCI network card or whatever? This value is what's currently... The set of instructions will load the value of bar 0 into the AX register, which typically contains the base address for the device's memory mapped IO space. Do we have any idea of what we might expect EAX to be at that point? What should bar 0 be? Let's find out. Okay, so we're going to do run.sh, and then we are going to break at 2C. Okay. We don't really trust the disassembler at this point. It's disassembling 32-bit assembly. We don't have 32-bit assembly. We have 16-bit assembly. But either way, we are at, in fact, we're going to not trust it so much that we're going to say at this place, really I want to go to the next instruction, 2E. I want to do commands, EAX. We'll say silent end. This is what came out. FEB 80000. What does it think? Okay, the bar base address register indicates whether the device maps its register to memory space or IO space? Okay, this must be called memory space. CF8 must be an address within, or with an IO space, an IO mapping. Okay. I think we got a 0 back, assuming this is the right thing. So that means memory mapping. Memory makes more sense than IO to me, but we're getting a little comfortable with this. I wonder if that's correct. Is this IO mapping? Like, this is IO space? CF8 is an address in IO space? We're going to assume that's true. The rest of the bits in the bar after the least significant bit provide the base address for where the device's registers are mapped. For memory mapping, this is typically assigned to certain boundaries, e.g. 16 bytes, 4 kilobytes. So some bits, lower bits beyond the LSB might also be 0. Okay. Oh, look at this, FEBC0. Is this what I got? No, I got 8000. Well, it's close. Okay. Registers to a default starting address in the guest's physical. Something like that. Can vary. Okay, we'll assume it's vary. How do I know that it's correct? So I know that we are looking at bus 0, device 3, function 0, bar 0, whatever the heck. How do I know that this is actually my E1000? Mask out lower 4 bits if it's memory mapped. I don't think we need to do that because it's already zeros, but it's a nice idea. Okay, so here's the question. Okay, so I did, and I got back in EAX. How do I know this is actually my E1000? Like, I'm not totally convinced. What if we were like looking at other hardware or something? From bar 0, after querying the device at bus 0, device 3, function 0, after does indicate that you have accessed a PCI device's base address register. To confirm that this device is indeed the Intel E1000 network adapter you intend to configure, you should check the vendor ID and device ID from the PCI configuration space. Okay, how do I do that? These identifiers are standardized and assigned by PCI SIG to ensure each device. Okay, I believe that it's uniquely identifiable, but how do I identify? CF8. Isn't that what I was doing before? CF8? Yeah, CF8. Okay. To read vendor ID and device ID. Wait, but I don't think 1.8. So this device 3 offset 0. So this, they're saying switch this 1 to a 0, offset 10. So is bar 0 at offset 10, but vendor ID and device ID are at offset 0. Also, we should copy this real quick, because I like this. We are going to document all of that because that right there is a magic number. We are going to change this, in fact, to a 1 or 31. Because that makes more sense. Okay. Just going to let that roll for now. Okay. So to 10 for bar 0, but instead now we're setting it for, we're going to set it to 0 for the vendor ID and stuff. We bring it in, shift right EAX by 16. Now the device ID. Okay, let's just look at this value that comes back. So instead of cool, I think basically what this is saying, so this is the register offset. Set to 0x10 or set to 0 for, what's it called? The vendor ID? And device ID, we're getting both for vendor and device ID. Okay. So let's go ahead and make that be a 0. Correct our comment. Imagine a lot of this is going to change once we understand that things make sense through GDB. Continue. Okay. This looks very promising. 8086 came out and a 100E. Isn't that what we were expecting? Yeah, that looks good. Who says what it should be? It should be 8086 somewhere. Yeah. 8086 came out in those right there. 100E came out there. Cool. So the device ID is up top. I didn't know you could use 32-bit registers. This is also news to me. We're just using 32-bit registers like we don't care. Cool. Can I do comparisons against a 32-bit register, or is that really gonna draw the line? Okay, so now we kind of want to like, what do we want to do? We want to like assert that this is true somehow. What's the best way to assert this is true? Well, let's start by making it be its own function. Okay, we've got print character, keyboard, ISR. Okay, we've got our two ISRs chilling out right here. So I'm going to get rid of the space there. Cool. Let's go ahead and make a function right here, which is going to be called like init E1000. And what we're going to do, we're going to take all of this. We're going to put it there. The very last thing we're going to do is we're definitely going to ret. 31st bit. I don't know why we need the enable bit, but we'll roll with it. I still don't even know really what a bus is versus a device versus a function versus a register offset. So we're going to say vendor ID is an 8086. Device ID is 100E. Hold on, is there like an instruction for killing the computer? Is there, I thought halt just halt. Is there an instruction that will turn off the computer? Probably is going to be some other PCI or out instruction or whatever. I want to assert and I want to just like turn off the computer if we're wrong, basically. Yes, there is. blah, 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 blah. You know what? Something tells me I don't want to do this. Just kidding. We're not doing that. Okay. Let's just do this. We are going to this is my PCI configuration address. Maybe we'll create another function. Hope we don't get too crazy with functions. Read PCI, and what we're going to do is we're going to make this function just abstract away some of this. So it'll just take in an argument over EAX, and what it's going to do is it's just going to do out DAX EAX. It's also going to move DAX 0xCF8. That's also using CFC, right? CFC, we always use CFC. And then move dx 0xCFC. And we're going to do in EAX dx ret. Okay, so given, what should this be called? Does that make sense? What should I name this function? Specifically, it reads a PCI address. You know what? We don't need this. We don't abstract when you don't need to abstract. We're not abstracting. Get rid of this. Okay, here's what we're gonna do. Here's what we're gonna do. We're gonna say this. We're gonna make this be enable. This is bus. This is device. This is function. This is register. Okay. And what we're going to say is register 0 is our vendor ID. What's it called? Our vendor ID and our what? And our device ID. Device ID. Register 0x10 is our bar 0. What the heck is bar 0? What exactly is bar 0? Base address register. Okay. Cool. Used to specify the memory or I/O address ranges the device will use for its operations. Each PCI device can have up to 6 bars. From bar 0 to bar 5, they're used to map the device's registers into system memory, blah, 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 blah. Okay. So That is that. So we're going to do this. We're just going to say assert EAX. This is just going to be a comment, which isn't very reassuring. We're not going to crash if this doesn't hold true, but we're going to have this as a nice little comment until I can think of a better way to define an assert, which eventually we need to figure out how to turn off the computer. And once we have that, that'll probably be it. Cool. Now what we want to do is move EAX we don't need this. It's a little wordy. I don't even think we need this comment. I think we know that. And I think we know that. We understand out and in now. I think well enough. Maybe we even say just one comment here. Read PCI configuration from from this. Less comments. We don't need comments. Comments are overrated. This is going to be good enough. Okay. Now we want to do a similar thing, but instead offset 1, 0. I wonder if we even say like from PCI and then we're going to read bar 0 cool. Read bar 0 from PCI configuration. Here's how we do that. We do this and we change our offset to be 1, 0. And now right here, we want to break. We want a breakpoint. I don't even think we're calling this function actually. Hold on. We need to call this function as well. Let's do init E1000. We're going to put it in our loop just so that it keeps getting called. Call init E1000 so that we can set a breakpoint on it. Since we don't know how to set a breakpoint at the beginning of stuff, but it's good enough for now. Init E1000. Really, I just want to break on this ret. So 7.4 is my offset. Debug 7.4. We want to read EAX. Cool. And then continue. Cool. Okay, so that is that. Now the question is, what do I do with this thing? Okay, so cool. We have as bar 0. How can I read some packets now? Stuff to initialize this NIC, I guess, and set up its receive structures. It really likes to caveat the fact that we're working in a bootloader and that this is terrifying. Why? Just do it. Configure, reset the NIC. Right to the device control register. It's typically, okay. We have to initialize our receive structure. So I've always heard people say like RX. And what's the other one? Is it TX? Is this probably the same sort of thing? Receive descriptor array. This array holds the information about the receive buffers. Each descriptor points to a receive buffer where a packet can be stored. Okay. Receive buffer, actual memory locations, incoming packet setup. Guessing it's going to be like a ring buffer, like some sort of like queue thing where like data just magically populates based on things to see. Configure the receive control. Okay, how do I initialize this? Set the receive control. Initialize the RX structures, enable interrupts. Optional, depending on whether you want to use. Cool. Let's see some example. Oh, what is this? You were so close. Now you're writing C? I don't want C. Whatever, I can read C. Maybe I can write the assembly. Offset. Is this memory mapped? Am I like now doing memory things or do I need more in outs? Show me assembly, not C. Yeah, it's at some offset, but offset of what? Setting using the base address obtained from bar 0. Okay, maybe it is that. So is it just memory map to configure now? So for example, we have Feb 8000. Well, you're saying that is not mine, but we'll roll with it. A number of descriptors, size of each descriptor in bytes. Okay. TB. Well, I gotta allocate space for my descriptors and my receive buffers. Okay, the next thing we're gonna do is we're gonna move bar 0 plus this address. Okay, let's do that then. Plus what do you want me to add? Add control 0. So the very first address. Pull from memory, 32 bits. Can I pull 32 bits from memory? Let's see what happens. Let's pull from memory. Move EAX, EAX. Does this work? I don't think this is going to work. It works. 7, 8. That's where we want to break now. What is EAX? Whatever that is. When I pull from, I get, what is that? So now we also got to see what the heck this 26th bit is. And then I think, okay, we're just going to do that. Here we go. This is my control register bits. Bit 0. 0 is half duplex, 1 is full duplex. Bit 3. I don't think I have these enabled turned on like this. I think it's reading this backwards. Okay, this is auto speed detection. Okay, here we go. Yeah, decode it. What do I got? Set 1, indicating the link is forced up. What does that mean? 18. How many bits do I got on? I got a bit, another bit, another bit, another bit. So So I got 1, 2, 3, 4 bits on. You only showed me 3 bits. Okay, whatever. Bit 6. Yep, definitely true. Set to 1, indicating the link is forced up. Bit 18, the bit is set. Depending on the specific model and revision, this might indicate an additional feature or setting not covered in a basic overview. Check the specific data sheet. At some point, I'm going to have to look at data sheets. Bit 22, this indicates that the physical layer has been reset recently or is in a reset date. Okay. Either way, what it wants me to do is set bit 26. Do we already have bit 26 on? According to it. Hold on. Here's what we're going to do. Python and 126. Is the 26th bit on? No, it is not. Why are we turning it on? Set the reset bit to reset. Well, let's do it. You want me to OR EAX with that thing. Let's even copy all of that. Okay, and then what do I want to do next? I kind of want to pull out of memory again. Do I have access to like EBX? Can I write to EBX instead? Please tell me I have EBX. So then we want to OR EBX and then EAX EBX. Please tell me this works. Please tell me I don't have 132-bit. Oh, I got another 32-bit register. Sweet. Okay. Now I want a breakpoint right at 8.3. GDB. What was it before? FEB8. Oh wait, I lost it, but I'm printing the wrong thing now. EBX. Before I had this thing. So I definitely turned another bit on. Right? Is that the 26th bit? I assume that is the 26th bit. Yep, that's the 26th bit. Okay, so I set the reset bit. Then what? My RX, okay, so we need a piece of memory and a number of descriptors. So I have some number of descriptors. This says I have 8 descriptors, which according to my knowledge of Linux of what a descriptor is I think it's just an opaque value. It's like a, like you have a file descriptor, which is just 0, 1, 2, 3, 4. It's just, you need a number to differentiate these things. Probably that's what descriptor means. Some sort of opaque value, hopefully. Set up descriptors. Set up each descriptor. Wait, where was I? Okay. So we take, okay, so we're loading effective address. So this is where I want my descriptors, number of descriptors. EDX is being set to 0 for descriptor setup. RX buffer plus EDX times 2048. So each of these things is 2048. I think that means my packets probably can be size 2048, maybe. Makes sense that we need at least that much space, though maybe even more space. But maybe that's the default. RX buffers plus this. Set up each descriptor. Set buffer low address. EAX. What are we doing here? EBX. Oh, descriptor size. How big is a descriptor? 16. Need 2 bytes to represent a descriptor. Is that true? Or is it 16 bytes? Getting 16 bytes. EAX. Okay. ADX RX buffers plus EDX. What's EDX? Okay, the 0th descriptor. Okay, so the 0th descriptor, this is probably going to be in a loop. Set the buffer address EAX. Okay, so in the descriptor, the first 4 bytes represent where the buffer is. Set the buffer, at least the low part of it. Set up buffer address high if 64-bit addressing. We are not, so 0. Set the buffer length and status. 0 seems good to me. Add EBX descriptor size. Okay, go to the next descriptor, inc EDX, go to the next index, pair EDX with ECX. Did we ever? Yep, ECX, jump less, go to setup descriptors, we're looping. Okay, makes sense. So we're setting up all of these descriptors by basically just saying, where are we storing data? Okay, so this thing is just a bunch of, these descriptors are just a bunch of pointers. Technically, they're also buffer length and status. I'm a little bit skeptical about that being 0. We probably need to tell someone that something's 2048. Do we, is this a hallucination? Do we need to put 2048 somewhere? A little concerned about that. Set up the receive descriptor base address. RX descriptor goes into EAX. Okay, we're about to write to bar 0. Okay. Is there always exactly 8 descriptors? Our read bell. Okay, put that in there. 0 into. Okay, sure. Right, because we're doing 32-bit addressing here. 16-bit, we're still in 16-bit mode, but we're able to do 32-bit addressing, it looks like. Which kind of makes sense, at least with segment registers, we definitely can, but it looks like we can kind of do it a little easier this way. Set up the receive descriptor length. Number of descriptors. So we're saying that there's 8 descriptors is what we set up anyways, and we're about to tell someone about that. Multiply by the size of each descriptor. Each descriptor is 16 bytes long, so we're just doing a multiply of 16 basically. And then put that into that. Okay, so we have our length, we have our length of our descriptor thing, I guess. Enable the receiver, set up buffer sizes, etc. Okay, is this 2048? That looks like 2048. Nope. Enable the receiver, set up buffer sizes, etc. Don't know what that means. What is this number? Okay, and then we're going to pull. Current head, yeah, ring buffer thing. Okay. So I think there might be some hallucinations in here that we're going to have to fight through, but I think I get the idea. We got to configure stuff. That's just how it is. Let's configure some stuff then. Okay, so we did this. That's cool. So right now we're just using EAX as my bar 0. EAX is my bar 0. Okay. We're going to say this is the device control register, just so we know what we just pulled out. Oops. I know we're just adding 0, but I think it makes it a little bit clearer. Maybe we even say device, or maybe we say bar 0 plus 0x0000 is our device control register. And then we don't have to say that, but we're going to keep that in. Okay. So we did the reset thing. We reset the nick. Don't know if we need to do that, but we're going to do it because it told us we got to do it. Can we set up like a place to start storing these things that isn't like, I want to store this stuff somewhere. Can I just like pick a place to store stuff? Is that sketchy? Can I just declare that I own an address? Wonder what's going to happen if I do that. Let's try it. What's the worst thing that happens? Okay, maybe we even do ECX for this. Or even EDX? Do we have all 4 registers? Looks like a yes. Okay, I want to like declare memory. So what I'm going to do is I'm going to say move EBX. What is a cool sounding address? 4242 12 42 00 and then 1234. Move ECX 0x4201. Can I just own these memory spaces? Here's what we're gonna do. Move EBX, comma, let's take EDX and right there. We're gonna test this. Here's how we're gonna test it. And then move EDX, EDX. Now what the heck is the value of EDX? Is that something other than 0? Time to find out. Do I just have memory mapped to me that hopefully no one's using that? Probably should be a little more careful about what I decide to use as my memory locations. But right now we're just going to YOLO it. 9A. 9A is now where we're breaking. And we want to know EDX. Something's there. Is that what we expect? Maybe we also break before. And see what is EDX right here at 8B. Do we need continues? We do need continues. At least they continue right there. Now, what are the odds that that is a good idea, whatever the heck we just did? Something tells me it is a bad idea. I don't think we're getting what we want to get. So we took EDX, which we definitely checked is at 8B. We checked the value of EDX, which should be this thing, which should be this. And then we are taking that thing and we're throwing that into EBX. Oh, this is sketchy. This should also be EDX. That could explain that confusion. Okay, well, this looks more correct. That looks like that value we were getting before. What am I reading out of memory? Okay, let's talk to ChatGPT. Instead of segment.data, I don't want that in my bootloader. I want to just know some nice locations that I can use as free scratch memory. Below the 1 megabyte mark. Is often considered safe for temporary data storage before the operating system is loaded. However, the upper part near 7C00 is typically reserved for the bootloader itself, especially if you are writing. Okay. It is generally safe to assume that 7E0 to around this. Cool. Unreal mode briefly. We're still in real mode. Just above. Use the stack. Let's use this region of memory, 7E0. Yeah, I like that. 0x7E00. 0x7F00, right? We only need hex 100 bytes here-ish, right? We need 16 bytes. How many do I need? I'm going to create 8 descriptors. 8 times 16. 128 bytes, which means, yeah, that's enough room for that. Let's try this. I kind of like it. Living life on the edge. This is my memory now. Why does that not do what I want? Move EDX 0x1234. EDX goes into EBX. EDX is zeroed out. Then we take that. No, this should be EBX. That's the issue. All these typos. Okay, look at that. Beautiful. Maybe, I think. I think our breakpoint's set wrong now. A0. There we go. 1, 2, 3, 4. Okay, this is my memory now. This is what I'm using for my bootloader. If I do a section data, hold on. Is a section data not actually filling in the bootloader? Is this like a BSS? Is section data fine though? Is that not going to take up bytes on disk? But then how would it know to reference it? What was it using before? Let's test it real quick. Segment.data. And then we were, here, let's try it. Let's try it. I don't know if this is really the way to write this, but test dba. If I reference test instead, offset test. Is this gonna assemble first of all? That's the first question. Nope. How do I do this? Who's complaining? Oh, does this need to be dot segment? No. Line 84. Thought there was like something like offset. Did we decide that's not true? That's like that. It's like that. Let's just try it. Test undefined. Okay. Test. Okay, that worked. Now what the heck is this test thing that I just created for myself? When we do this, where 66BB 66BB 7E00. Is that correct? 7E00. 7E00. I think that might actually be correct. 7E00. And then the next guy is going to do 7F00. Okay. Well, I guess we can test. Does this work? What do I want? I want a breakpoint at A0. Okay, we've got a breakpoint there. Oh boy. Oh, we didn't run it. Run.sh. Okay, I think this works. Let's roll with this. We want this. So we want, I think this will work. Can I do this? All right, I'm worried about like the assembler and stuff, that stuff is doing what I want. I think this is automatically, in fact, doing what I want. I think it somehow has decided. So for example, actually, here's what we'll do. If I assemble this, warning, byte data Byte data exceeds bounds. Okay, well maybe we don't need. Oh, I see. Yeah, I think this is the issue. I think if I got rid of this guy, it wouldn't say that. Yeah, it doesn't. The issue is I'm going past. I think the assembler is on the same page as ChatGPT about this thing, this maximum address. And probably we're going past it. So for example, we can test this. Or we can do the math. How much space do I have here? Um, 2, 9F, so A 0, 0, 0 minus, why do I need to do it that way? Okay. 7E divided by K, but it's saying each one of these things is 2048. So I got room for like 4 of these things. Can I have 4 instead? Maybe we can have 4. Let's try and have 4. Number of descriptors, 4. This will do that. We've got RX descriptor. And then what else do we want? We want this. Okay, I think this might actually work. Num descriptor, db descriptor size. So this is saying give me 16 bytes times 4, saying give me 2048. Okay, I think. What if we say also like buff size? Can I say like equal 2048 and do this instead? Then say, oh, I can't. Why did it automatically add a period? We don't like that. Don't think we need these comments. Okay. What happens now? Bet this will assemble. Oop. Didn't I say that we have space? 7E00. What if we say 2 buffers? 2 buffers. You get 2 buffers. Still? What's the issue? What if there's 1 buffer? 1 buffer. No, it still exceeds. Why did it exceed? Well, it's gonna go into a negative number. Is that why? Let's see here. Because of my segment.data. Let's see if it can tell me about this. Oh wait, what happens? What do we do, by the way, with our stack pointer? Where is that thing living? Do we set up a stack? Maybe we didn't. Okay, we didn't set up a stack. Tending exceeds the allowable byte size for the data type. Here's what we're going to do. We're going to stop playing this game. We're going to make it real simple for ourselves. None of that. That's all gone. Let's go back to here. 0x7e00. We're going to handle it ourselves. X this plus 2048. This goes to, actually, instead, let's go to 80. So it's easy to see. 80. Okay, and then this means is this is going to be my descriptors. Also, I haven't monitored chat. Well, let's make sure nothing popped up. Oh, I did have messages. We see people saying hello. Well, hello to all of you as well. Okay, so we've got this RX buffer thing. Okay, we need to set up our descriptors. So this is my descriptor. This is where my descriptors are. Are they called RX descriptors? RX descriptors. And this is going to be my RX buffers. I am just picking this. And the next buffer will be 2048, so it'll be over here, and then the next one will be here, etc., etc., etc. Okay, this is where we're storing things. We'll see how many buffers I decide to have. So right here, can I do that equal thing actually? What is the syntax for that? Is this just like a pound define? Let's do that instead. RX descriptors is right here. Okay. And then RX buffers. 0x800. Okay. Somewhere in memory, right here. So let's go back to EBX. Okay, EAX, we cannot mess with EBX. Or EAX. EAX will always contain bar 0. Okay. Next thing we need to do. So we reset the NIC. Oh yeah, then let's do this also. Let's take all of them. Then, cool. And now we'll add a space. Good enough. Okay, then we'll get rid of that. And we will say plus the control. Okay, now our code's more documented. And this is reset the NIC. Okay, next thing. Set up the RX descriptors. This, instead of this, we're just going to put that. I don't know that that's going to work. We also need to say how many descriptors we got. Got this many descriptors. Really, we're going to say we got 2 descriptors. RX descriptors. We're taking that address. Okay, so what this really means is just move EBX RX descriptors. Okay, and then we move ECX, the number of descriptors. We zero out EDX. All right, and then we got this whole business, which we might need to clean up a little bit. Set up each descriptor times 2048. Is there not something buff size equal 0x 2000? Wait, is that right? No, it's 800. Yeah. Equal 800. Cool. Can we do that instead? Oops. Buff size. This. I'm skeptical about this guy. Descriptor size. 16. Move to the next one. This. We didn't touch EAX. We did touch EAX. Well, that's sad. Don't go messing with EAX. Okay, EBX got taken by this. ECX got... Okay, we ran out of registers, at least of A, B, C, D. Okay. So we've got RX buffers there. EDX buff size. This. Descriptor size goes up. EBX. EDX. Do we need EBX to be storing this? I don't think we do. I think we don't. Let's do load effective address EBX right here. And then instead of EBX being this, we're going to say this EBX. Plus so this is the base. So this would just keep doing that. We want this. So this is the base plus will it resolve this? EDX times disk size plus 0. Because this should be able to fold in with this constant. Let's see if that will work. Or if I have to rewrite this a little bit. I think it should work though. Yeah. let's see here. Let's assemble this. Nope. Invalid effective address. On what line? 109 and 110. 109 and 110. RX buffs. Why is this bad? Let's see. If I did this, can I do this? What if I did like EDX times buff size 0x800? Does 109 still not assemble? Yep, still does not assemble. If I did this, 109 now assembles. What if I do times 100? 109 does not assemble times 8. I thought you could do something like this. Maybe not though. What if I say dx? Really? I can't do this? Like sort of dl times 8? Why can't I do multiplication? dl plus 4? What? Okay. Here's what we're going to do. We're going to do it ourselves. What needs to be written where? Can I say move this plus 0 EAX? Does 103 assemble? 103 assembles. Plus 0 is EAX. EAX. Okay, what do we want to fill this in? I'm just going to get rid of the loop, basically. We're going to just one descriptor. We'll have one descriptor. Maybe we'll have two descriptors by hand. EAX. EBX is what again? Our descriptor. And this EAX is our buffer. Okay, so where is our buffer? Put that at the descriptor. Plus 0 is going to be that. Does 103 assemble? 103 assembles. Okay. How does it assemble? How about my bootloader.lst? Oh, we stopped assembling. Great. Okay, let's get rid of all this. That way it assembles. Operation size not specified. That is what I was expecting to see. Word pointer. Can I say D word pointer? Will it let me do that? Well, as a D word. Sure. I think this is cool. So there, and then at plus 4, we want a 0. It's 4, we want a 0. This is the high address. No high address for us. Okay, at +8, it wants a 0. Oops. It claims, I think we're also just going to say +12. Hold on, here's what I want to know. Is buffer length really 0? I'm skeptical about that. Is indeed incorrect, yeah. How much data it can safely write to the buffer? Yeah, exactly. If each buffer is 2048, I don't know. Can I have a smaller buffer? Can I only accept packet sizes that are like 256 or something? Does that not work? Yeah, that's what I expect. Clear the status, set the buffer. Cool. Okay. So here, whatever, we'll roll with 2048. And we'll give myself 2 packets worth of space. Cool. So we set up this descriptor, but then I could also do 16. Actually, can I do plus 16 times 1 plus 0? Is it willing to figure that out? It is. That's how I'm going to write it. Plus 0 times 16. We're going to write out my indexes also. Okay. Look at how crazy this looks. We're just cutting out the loop. Who needs a loop? Index 1. And then buff size. Buff size. Plus 0 times buff size plus 1 times buff size. Okay, now I think I set up 2 of these things. Still have to write to some sort of control thing. And I will once again check if there's comments. Your website. Oh boy, we got a whole bunch of people that rated. Well, we didn't pay attention to that. Okay, so next thing we're gonna do, we're getting this networking card slowly but surely set up in a very probably unnecessarily complicated way, but we're gonna keep rolling with it. Okay, we don't need our loop. Our loop is gone. Okay, now set up the descriptor base addresses. This is what we want to do now. Okay. We don't need to do that. This is going to be EAX plus this thing. So EAX contains bar 0. EAX plus that thing. And instead, we are just going to do that. Cool. Set up the descriptor length. Sure. And we will do EAX plus E100 num descriptor times 16 times descriptor size. I think that works. Enable this thing. Something's got to go here. We are writing to that thing, EAX, this thing, example, set appropriate bit in RCTL. What is this bit? Why that number? That does not make sense. I mean, I'll do it, but R0 RCTL. What bit number even is this? 4, 8, 12. Is that like the 16th bit? Or is it the 14th bit? 14th bit. Enables broadcast accept mode, which means the network adapter will accept all broadcast packets. Is that true? Is that really the 14th bit? I'm so bad at reading bits. 14 hex. It is the 14th bit. I don't know. What is a broadcast packet? This setting is essential in certain network environments where broadcast traffic is crucial. You say so. Oh, wait, we can also set to 1 to enable the receiver. I might want to do that. Where the heck did I go? Okay, hold on. What is this offset? RCTL. Can I get what the current value is? Let's just do move EBX. This guy can chill for a second. Oh, forgot our operation size. I think all of these guys were D words, right? Where was that? Yeah, they're all writing, they're all using EAX, they're all D words. Okay. What is this thing? Let me see what EBX is at that point. EBX. EBX, F7. At F7. What is EBX? GDB. It is 0. Really? Okay. You say so. 7C F7, right? F7? F7. What is EBX? What is EBX? Okay. So let's go ahead and say we want enable receiver bit. Receiver bit. Store bad packets. Wait, what? Bit 1. I don't think this is bit 1. Oh, there's bit 0. Bit 1. Receiver bit. What are all my RCTL bits? I think ending with a 2 means you set store bad packets. I'm pretty sure that's not. So do I really want broadcast accept mode? Receive buffer size. I didn't set the receive buffer size. How the heck do I do that? Wait, didn't I put it in the descriptors though? Yeah, I put it in the descriptors. Set the size of the receive buffer. Why is it also there? And why does it only take 2 bits to do that? To pass all. Do I just want to turn everything on? Reception of, I probably can't handle jumbo frames. Set 1 to accept all broadcast packets. Path duplex path. There's a lot of options. Do I want store bad packets? What the heck is a bad packet? Packets with errors are discarded. Well, I guess I could decide. I guess the hardware is going to throw out bad packets, basically. I don't think we need this broadcast thing on. I think we just turn receiver enable on. Let's just write a nice one. Receiver enable. Enable receiver. Here we go. Enable receiver. What were my other things I did? Should probably document some of this a little bit. Got a lot of magic going on here. Set up the base address. Here's what we did. Set up RX descriptors. There you go. Who needs loops? Set up the base address. Receive descriptor length, I guess. Wait, this is this right here. This is, wait, I wrote a 0 also. Oh, right here. Okay. Descriptor length. And enable receiver. Okay, here we go. I think this just configures everything. And then this says you can pull. Let's just do a polling loop then. Polling for packets, simplistic version. Okay, this is EAX. This is EAX. Read the current head. Okay, that makes sense. So we can pull from this part of memory. So remember, this device is like memory mapped to EAX is pointing at like this special memory location that has all of this stuff. So this is going to tell me right now if the current head and the current tail are the same, which means there's no new packet. Otherwise, okay, this is how we update the head. That makes sense. This is where we process the packet. Okay. This is where we would update the head to say, sure enough, we did it. I don't know how we deal with the whole modulus thing. This probably has to be a ring buffer, and this is going to be a disaster. Once it's just going to be it is going to be a problem. But I think it should handle one packet. We will put a NOP right here. And we'll break at this NOP and see if we can use GDB to figure out what the heck kind of packet I got. We are missing D word, D word, D word, D word. Shouldn't it be able to infer that? This one it can't infer. No, it can. Who can't it infer? 1, 2, 2. This guy. Oh, yeah. And that. Enable receiver. And then we go into our polling loop. We got a NOP. I want to break at this NOP. I want to see what the heck is going on here at this NOP. So add 1z blah, 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 blah. Here. And yeah. I don't think we hit this breakpoint yet. But maybe if I create a new terminal and I netcat at localhost or whatever, cd dev, actually we want space there, cd boots clear netcat localhost 4242 because we've got host forwarding set up for 4242. If I do this, did anything happen? Nope. Nope. No packets were seen that day. Let's also set up a breakpoint at this jump equal. We are in this polling loop, right? Okay, so at 10b, I want 10b. I want to print out move ECX. We're just going to do this. ECX, read the current tail. Compare the head and the tail. Polling loop. Okay, I want to print EBX and ECX at this point. But I got to reassemble because I don't know my address anymore. At 10b, or it doesn't really matter, 10b. Yep, 10b. Let's print EBX and ECX. Cool. Cool. Then let's do that. Let's do that. Let's do that. Why are they 0? Something tells me that's not right. Breed descriptor. Let's see how ChatGPT feels about this code. Let's get it in the loop. How do we feel about this? Okay, your assembly code for initializing and polling an Intel E1000 network card looks quite comprehensive, blah, 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 blah. Okay, yeah, I know I don't actually assert. Resetting the NIC. You are correctly set the reset bit. Make sure to wait or check for the reset to complete. How do I do that? You've set up the descriptor's base address and length correctly, or make sure each descriptor's status field is managed correctly. I think that's fine. Receive control, but you might want to configure additional settings such as buffer size, and configures buffer size. Okay, this looks like something I might have to do. Further explain this number. Memory. Sure. And then how do I also do this? How to do She wants more comments. Yeah, probably. Okay, this is yeah, this is correct. This is the binary representation. But this is unless bit 1 is that and there's also a bit 0. Maybe there is. Something tells me that's true. Strip Ethernet CRC in software. Set bit 22 correspond to a custom or less common setting. You need to check if the reset bit has been cleared. Well, you gotta check already if 126. Okay, we'll do that in a second. Let's start by trying, instead of 1, I have a feeling it's gotta be a 2. So we're going to do printf %x, %x, ebx, ecx, and a continue. Oh. We also want a new line. Okay, that's a lot of zeros. That's probably not actually what we want. We actually probably just want to break at 110. 110, and we don't want to continue. Can I hit this breakpoint? I cannot hit this breakpoint. Okay, let's try this magic number that it likes. Who knows, maybe it'll magically work. Just to be sure, that, no, that still does try and do something. If I kill this, though, that immediately, yeah, okay. 4242 should be correct. Should be there. I think I might have messed it up. Let's restart. Set up a breakpoint. Netcat. I think that would have already sent a packet. No. We are not getting our packets. Okay, let's try this wait reset thing. When we do this reset. I'm not sure that I need to do this. Not sure here what we'll do. We'll say to do. Not sure this is really necessary. We'll take its word for it and do that. Do that, we'll do that, we'll do that, do that, do that, oops. Do that. Oh boy. We moved 11D. And then we'll do that. I don't think we're getting my packets in. Where the heck are my packets? Where are my packets at? Who knows where my packets are at? Does anyone here know where my packets are? Where are, if I do this 7D08. Wait, what? I thought we had a breakpoint there. 7D08. 108, 108, 108. I'm in my polling loop, yeah. What is EBX and ECX set to? Wait, I don't think this can be 0. Okay, here's what we're going to ask. This seems like a bug. I don't think it's allowed to be 0. Would it make sense for EBX and ECX to come out as 0? I feel like that doesn't make sense. Oh, just kidding. When initializing, upon reset or initialization, when the reset card is, number card is reset or initially configured, the received descriptor head and tail are typically set to 0. No packets have been processed yet, pointing to the start of the descriptor ring. Empty descriptor ring. If no packets have been received since the NIC was initialized or reset. Okay. actively receiving data. Yeah, how do I debug this, or what could be going wrong here? So we're setting up. Can we pull out of memory here? Let's see here. XGX that. So we'll say 4WX. So what did I set this to? Size. So 16 bytes. How do I get a half of a word? Is it H? Yeah, okay. Okay, so right here, I wrote 8,000. Then I wrote a 0. And I wrote a 0. Why did I write a 0? Shouldn't I have written... This does not look correct here. Okay, here's what we're going to do to verify this. I don't think my descriptors are correct. I want to break... Where do I want to break? D8. I want to break at D8. 0x D8. Kill that. Reconnect. Oh. Well, we need to get rid of our polling loop. How do I do this? Comments. Toggle comments. Okay, here's what we're going to do then. We're just going to delete it. Or actually, even simpler. We're just going to ret right there. Don't even hit that code. The way I can see this get initialized over and over and over and over. Okay. This is RX buffers. So that looks correct. And then the next one's going to be that, which also looks correct. This is a 0. We wrote 0. Makes sense. Buffer size. This should not be 0. Nor should this. Nor should this. What the heck is this code? Where am I broken? Set up a breakpoint at D8, 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 right here. Right after we did all of this. Okay. Why does this have a 0 there? Okay, let's also do breakpoint at 9, 0. Let's reconnect. What the heck is this? PX this. Oh, wait, what? Oh, we are writing 32-bit. Yeah, okay, I was looking at this wrong. I see now. It's not a half word. It is, in fact, a word, and it's 8 of these. Okay, that's the issue. There. Okay. So this is 800. And then this is this. Mm. RX buffers is 8,000. Oh, there we go. I feel like 1, 2, 3, 4 bytes. Then we write a 0. Okay, I see. And then buff size. Okay, this is saying the buff size is 800. Yeah. Wait. This is what we're expecting it to look like. You confirm the RX descriptor struct. What is this thing supposed to look like? I feel like there's a chance that's wrong. This also doesn't necessarily make sense. Okay, so it is 3232. The length, the size of the buffer available. Yep. Wait, the length is a word. But that's fine. The result of the checksum, the status, errors, blah, 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 blah. Okay, that's fine. We can ignore the rest of that. Yeah, that looks fine. Confirm what should go at this thing. Oops. This thing. This thing. And this thing. Got a feeling that the receiver is not turned on. These registers hold the 64-bit address of the base. This descriptor should be aligned to a 16. Okay, this looks correct. The lower 32 bits. ALAH. Right, which makes sense, RX descriptors right there makes sense. Right, this looks correct. Total size of the descriptor ring calculated as the number of descriptors multiplied by the size. Okay, we've got 2 descriptors. They're each 16. So that looks correct. If you had 32 descriptors, it would be that, but I don't. I got 2 descriptors. Receive control. This is another number. It keeps changing numbers every time I ask it about this thing. Okay, let's try this magic number. Get rid of the ret. Assemble. Which means I now want to break at 11D. 0x11D. If I attach then I hit that. Why can I not? We're never messing up EAX, right? No. Um, okay, EAX is still. Wait, what do you mean 20? Who the heck said 20? I don't think that should be 20. Did someone mess up my EAX? Okay, what is it right here? At 90. And then we also need a Rets here again. Okay, I feel like my EAX is getting messed with. I don't think it's supposed to look like that. EAX looks chill right here. Who adds 20 to it? Someone's messing my EAX up. Who is messing my EAX up? Someone's messing it up. When? Wait, where am I? 08 108. Yeah, we're right here. I don't understand who the heck messed up my EAX. Who's messing my EAX up? Okay. Let's put the red back. And I want to break. I'm going to break at 105. I'm going to add a NOP right here. It doesn't really matter. We don't need a NOP. Let's break at 105. Oh, I want 105. What is 105? Maybe I want 108. Do I want 108? 108, 108, 108. Let's break at 108. Wait, where am I? Let's see, 1E. We're way over there. This is fine. Cannot figure out why my EAX is changing. I want to break right at 118. I got a feeling I might know where it is. Is it getting messed with by one of my interrupts? Okay, we're going to get rid of this STI. No more interrupts. Okay, this is what we're going to do. I'm worried it's an interrupt that's doing it. Probably a little sketchy to have these interrupts on. 116. 116 is where we're breaking now. Gonna do that. We're gonna do that. Okay. Okay, that is now the correct value. I bet that's what it is. One of my stupid interrupts messed it up. Okay, because guess what? Move AX, tick count. Yeah, I bet that's it. Okay. And so now we disabled our interrupt handlers. What do we want to do now? We want to, okay, 1.6 EBX ECX. Okay, that's fine. Okay, now where we really want to break is at this 11B. And then maybe it's going to be working now because now we don't have our addresses all messed up. Oh. BSD 1B, 11B. Hmm. Okay, let's mess back with this one magic value. Still the magic value in here. Where's my magic value? This guy. What are all these bits? Tell me all the bits of... Tell me all the bits of this. Is there a 0 bit or do we start with the 1 bit? I'm going to turn everything on that makes sense to turn on, or even remotely possible to turn on. Let's see here. Bit 0. Okay. Receiver enable. I think we can just set it to a 1. But I think we don't have a 1 on. Okay, store bad packets. Let's store that also. Enable passes all. Okay, we're going to do that also. Let's turn all the bits on that might even slightly help guarantee I see the packet. What the heck is a broadcast packet? So I'm thinking we want this bit on, like all of these bits on. Unicast passes all. Like we don't care about destination MAC. Just on the off chance someone got a bad MAC, I want it to. Enable. I want all of them. Definitely, it needs to be an odd number though. It's got to end with a 1. Tell me the number. Tell me the hex number. Oops. Store the bad packets to receiver enabled, blah, 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 blah. Okay, while it's figuring this out, I'm just going to try one more time. 1B is correct, right? 1B. Sure is. Didn't hit. This is my number. This thing. And confirm where is just going to turn that on. RCTL is at offset 100. This guy agrees. Next thing we might want to do is see what the default value is, maybe, possibly. One B is still where we want to go. EAX. Where am I? 106. 106 is this guy. X100 BX EAX. 2048. Bunch of null bytes. Whole bunch of null bytes. So it makes sense. Wait, I did write something. Where is this? 801. 100, 100, 100. Why don't I see it when I do that? Hmm. So this is there. What did I write here? Control. We wrote that thing. The device control register and then the receive control register. 81. Okay, device control register. And then there's a whole bunch of random stuff here. What is all this stuff? 81 F7 81F7. Okay, we wrote that there. Are these things really this far apart? Device control register. Did this agree where the register is? In bar 0. Hold on, can I switch over to 40 again? In bar 0, what are all my values in this memory? The next one is the status register. Okay. So this is my status register. How big are these things? Probably they're 8 bytes, 4 bytes, I don't know. Maybe 100 WX. 100, we set to that. Plus this. 7E0. That address has these things. Okay, I think this is all set up correctly. X10WX there. There's no bytes there. Bytes didn't magically show up. We also have transmit registers. The read length, 32 descriptors, 16 head, 81. This just is not working. What the heck? RDH. RDH 2810. 2810 for RDH. Yep. Is it possible to just have 2 descriptors? Okay, now we're going to try GPT-4o. See if it can analyze why the heck this is failing. It says you can. Okay. Let's try it again. This. Okay. I am never leaving my polling loop. Why is this failing to see packets when I do, like, localhost 4242 from the host? Sure. Polling. Verify bar 0. Okay. Pretty confident about bar 0. Pretty sure this looks good. Ownership bit. What the heck is the ownership bit? What the heck is the ownership bit? Am I missing that ownership bit? Okay, that goes there, that goes there. Enable the receiver. Receiver, and this thinks it's a 2 again. What the heck is it? Ooh. This is doing that. Compare it there. Boom, boom, boom. This 42, 42. The heck is the ownership bit? It's not a concept. Introduce confusion. Doesn't apply here. Okay, so we don't need an ownership bit. No, we don't need an ownership bit. Changed its mind. Should I try this style? Packet. 0x2 is definitely receiver enable. Let's try that. Move bx e bx ebx. This guy ebx. Store bad packets. That. Fix this. It does this. We're decided to start storing things in EDI. Save bar 0 address in EDI. Maybe we'll do that, but I don't think it matters. Enable the receiver. We're checking this. All of these things haven't moved, right? 100, 2800, 2804, 2808, 2810, 182, 16, 800, 70, 00, 8000. Okay, I think this is all. It's all correct. Okay, we'll try this strategy. I might have to come back and look at this with fresh eyes another day. This is starting to take too long. Okay. Okay. This bootloader 1 to F. Do I ever hit 1 to F? GB attach. Seem not. 1A. 11A is this guy. What is EAX currently? And it is why does it say failed and then succeeded? Two 7001 4242. Okay, I gotta check the Twitch chat to see. Nobody has ideas in the Twitch chat. Wait, what the heck is this? Who decided to move that there again? We can't do that. Okay. This. 1, 2, 3. 1, 2, 3. Nothing. Absolutely nothing. Should I need anything besides or EAX0x2 to get my NK local 12700142242 to work? I'm like, I'm worried I'm doing something like super dumb. Feel like it's like basically correct, but it's just like ever so slightly off. You need to ensure enable the receiver. Hmm. Let's copy all of this just in case. Just in case something changed. So don't need that. 1, 2, 4. Show me bootloader code from scratch that will pick up a single packet if we do all x86. Let's see here. This is from scratch, E1000 in it. What do you mean? Show me full code. It just says read the docs. Okay. What are we seeing that it is? What? Oh, wait. EDI. EB. So I think it's at here. Okay. So it decides to do that plus 28 hundo base address. It's not even putting a length in. It's not even setting. Uh, It's taking... It's taking this and testing if there's a 1 there. Placeholder. I want you to fully write working code. Okay, we might also want to refer to this manual it keeps referring to. Let's see here. Where var 0. Oh boy. What are some other things that we have here? We've got the control. Okay, here's some things. Hmm. Does this talk about FEB? Nope. Okay, all of this stuff. Wait, was there... Read this, read this. We did this thing. Okay, let's ret here. What is my value again? So that's what I want to know. I want to know here. 7D, what is the value of EBX? EBX. Comes out of what does that mean? Set the RX descriptor head and tail. Am I supposed to do that? Is that why it's always coming back as zeros? I never like put them anywhere. Head. Descriptor. Tail. Receive descriptor tail. Something tells me that I should be initializing that. It's 26. Device is currently in a reset state. How do I... Okay, so something tells me that I'm like entering this reset state, but I'm supposed to leave it? Like, clear the reset? Oh boy. So I am responsible for clearing reset. Am I also responsible for setting up RX head and tail? Um, okay. Let's roll with it. Given these ideas, help me fix up. Okay. Head and the tail are there. This is resetting the nick. But then it's telling me not to reset. I don't understand pulling loop. PSI. IDI. Read the current head, read the current tail. Did we decide to move to EDI? It looks like we did. I thought we decided. Sure. I thought we decided when nick in reset state was bad and we had to clear bits. How the heck do I read this thing? Power up. That looks like a nightmare. Um, okay, what the heck is this value again? 26. And 26. Okay, the 26th bit is not set currently. 28th bit is not set. Okay, but then where am I? 1F. 1F is pointing at 1F, 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 1F. No. At 7D. 7D. I feel like I'm losing my mind staring at all this. I see the issue. 7D. I see. Okay. So at 7D, we have EDX. What the heck? EBX, which is that. And then I step, which means we turned on that bit. Okay. Why are we resetting the NIC? I don't know if we need to do that. Then we step. We're at 8.8. Okay. Yeah, I feel like control. Okay, what is this control register? Control register. Control. So something that talks about control. So it's a 0B. Auto negotiation. Why do I mess with the reset bit? Like, I don't understand what the whole idea here is of this reset bit thing. Sure as the NIC is operational and not in the reset state. Okay, so I mean, do I just never mess with this thing? Okay, let's try it. I'm like highly skeptical about this, but we can try it. Okay, it says EDI, is this guy? Yeah, okay. Okay. Then oh, this sets it to 0. EDI. Okay, so we initialize the head and tail to 0. I mean, this is setting it to 1 technically, I guess. So that is different. Okay, let's try it. Descriptor length. Let's see what happens with this. this is all true, I want to break it 148. If I get a packet, that would be awesome. Nothing. So we're at 133, which is right here. ADI is right there. Shouldn't these things not be 0? What is the read head RDH? But at some point that was not both 0, right? Because we... Okay, here's what we're going to do now. Let's go to 127. 127. Let's do that. Let's GDB that. Got to restart though for that to work. Actually, and we also have to do a ret there. Because this should be set to something more interesting. One, three, three. Okay. EDI is right here. EDI plus this guy. That guy is a 0. That guy is also a 0. What the heck is that? Okay, let's get all of this out of here. Kind of a bad spot for it. Let's do that. Does this still assemble? Yep. EDI is right here, plus the head. Don't understand. 133 is right here. Shouldn't this be like a 1 and a 2? Okay, here's what we can do. We can break right here. This should definitely be that. It's still not the case. 2818. I thought. Okay. 108 then. Zero B. This is now 1, which means that. So I'm going to step. Currently at 2D21, 2D21, which means it should have been set, but it's not set. EX is 1. And I wrote E. Why is there not there? And what's my RIP? 21121. I'm about to put a 2 there, but I already decision. How the heck is this not writing? I'm not getting my 1 written there. Stepping through in GDB, and it seems a 1 is not being written to RDT. Descriptor tail. Descriptor tail. Is there anything that talks about like initializing this stuff? Try 16 byte. Rates the tail register to add received descriptors to the hardware free list for the ring. Don't understand. So this clears the reset. This sets up all this stuff. Sets that up. Sets that up. Clears. Verify running the bootloader is properly taken out of the reset state. I think we're going to have to call it. I feel like we've been messing around with this for a long time. I'm starting to get a little bit tired of doing this. I think I'm going to need to come back to this with a fresh mind. This E1000 is no joke. It's more difficult. Much more difficult than the keyboard, it seems. Um, that's Ethernet Are we sure we need to clear the reset bits? Hmm. Maybe, is this Googleable? E1000, does it need to be reset on boot? How do I, what kind of E1000 is this thing? E1000, no, I just said that. On boot, bootloader. How do I even Google for this sort of thing? Bootloader code for E1000. Has anyone done this before? I assume someone's done this before. This is straight from Intel driver. Okay, let's see here. Reset hardware. E1000 right reg. Hardware IMC. Is it like an init thing? Who the heck calls reset hardware? This. Here we go. Okay, so it probes to find matching PCI. Malloc, blah, 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 blah. Memset. Hold on, I should zoom in. Assign the passed in values. Sure. Try to enable IO accesses. Mac and physical settings. Initialize general software structures. PCI read. Identify the Mac. Set media. Is that it? Like this didn't do anything. Okay, probably it's this. What the heck is the IMC? What is the IMC register? I need to clear this thing out. RCTL. Disable the transmit and receive units, then delay the complete before we hit the MAC with the global reset. What the heck is this? For resetting the device. So we read the control register, and then we issue a reset. Okay, so it does issue a reset. What is U delay? Is this like literally sleeping for microseconds? Control extended. Else. And read reg. ARP. Mink ARP. So this is something to do with ARP, maybe? E1000 read register. Are we also like control extension? Like we're also clearing out the extended register? What the heck is this flush thing? D8. I don't think I'm supposed to clear the reset bits. I think I'm supposed to set it while initializing. Clear interrupt mask. PBA. What the heck is PBA? PBA. Definitely some sort of register. Masking off all interrupts. Masking off all interrupts. IMC. The heck is the WUC thing? No idea what that is. List add tail hardware. Validate the EEPROM and get chipset info. ETH register. What did it think about that? You are correct. Let's adjust the bootloader. Disable all interrupts. Then we reset it. Still set, keep waiting. Okay, so I think we reset and then we wait for it to stop being in the reset state. Okay. I want to get this figured out. I feel like I've been on this for hours because, you know, I have been on this for hours. Let's get the base address save in EDI. Okay, this part is what we need to change. So we disable interrupts, we reset the NIC. Then we wait for the reset to complete. It's setting up the RX descriptors wrong. Are you setting up the RX descriptors correct? Don't we need a size or something? So annoying that I can't copy the code sometimes. When it's like typing out, you can't type code or you can't copy code. Sad. What is this descriptor done thing? That seems new. So we wait for the reset. PCI EDI. But you're still writing EDX EDI. Check if the descriptor done. Okay. Are we sure? Are we sure that ESI plus 8 should be 0? We want length 0 in my descriptor. I don't think that's correct. What is my 0xd8? We want to define E1000 IMC. This is interrupt mask clear register. Interrupt mask register. And then we do that, then we do that. This, that goes there. That goes there. So we wait for reset. And after we're done waiting for the reset, let's do this. Then let's build that. And we want to break somewhere. Where do we want to break? We want to break at this 12C. 12C. Did I write that to EAX? Okay, EAX definitely has that set. Step, step, X200GX ESI, or EDI, what is it called? EDI. This is bad. This logic just lost me my EDI. Did it leave EDI? You are clobbering EDI. Disable the interrupts, reset the NIC. It's on EDI now still. Set up this. ESI, yeah, okay, change the register. Okay, this part got fixed. Now my EDI shouldn't be messed up. Now let's run it again. 2C, 12C, 12C, 12C. EAX. Okay, EAX is still a 1, which is good. EDI is not messed up. EDI is not messed up. X100GX EDI. Got a lot of null bytes. Don't know if that's correct. What is at EDI plus the descriptor base? It's a 0. Something tells me that's not good. Hmm. Is it possible that GDB is lying to me? I feel like it's possible. EI plus that address. gx that plus. Aha. Yeah, why I don't know where this negative came from, but that is part of my issue. Okay. So my descriptor base address. Okay. X4GX, that address. I think that's set up correctly. And then RCTL. RCTL. It's 100. How is it already at 2? Does a reset not like wipe this out? Seems like it doesn't. Okay, here's what I want to test. Let's test. Does it work? We want to get rid of. Here's what we're going to do. We are, instead of loop, we're going to do loop, jump loop. So we should go into this endless cycle if we ever happen to do this correctly. $150 plus $150. Just not hitting it. Said we're at 1A3. Where are we? Oh, just A3. Wait. What? How am I there? A3. E4. One F. B5. Oh, we have this ret still in here. Has no chance of this working. Which means we want to subtract 1. Good enough. That's 4F. 1 4F, 1 For F, continue. Did it actually hit? One for F apparently just hit. How true do we think that's going to be? And we initialize the head and the tail not to point at each other. That's why I'm skeptical. How would we know if there's data in here? Oh, probably our buffer. Which is where again? Seeing a lot of zeros. Still seeing a lot of zeros. But we have hit here for the first time now, which does make sense. It should be able to hit here. How do I know when a... Check the status of the current descriptor. Oh, that works actually. Pulling loop. Let's try this. Descriptor. Let's try it. So how would I know now that something's happening? Take the RX descriptors, put it in there. Read this. If they're the same, we jump to polling again. Check the status of the current descriptor. Add EBX, EAX. What is EAX? The current head. Okay. By the size, yep. Move into this. Okay, this is where I want to break. 167. EDX. It's A0. Which I think means nothing. Hmm. Maybe I really want to break at 170. Okay, one more thing I want to try is just have like 4 descriptors. Nothing. All right, we are failing to get packets. We've been trying for several hours now. We are going to take a pause on this now, and we are going to continue trying another time. Hopefully, we can figure this out. Surely we will figure this out. But right now, we're not making progress, and so we're going to cut it here. Thank you all for watching. I'm sorry we didn't quite figure this out, but sometimes that's how it goes. You just gotta bash your head into the keyboard for a while and hope things work, and then sometimes they don't, but come back to it later with a clear mind, and hopefully we'll get things working. All right, thank you all for attending, and I'll see you in the next one. Goodbye.